In this video, we apply topics that we learned in the last several videos. Namely, in the last several videos, we focused on reactions of aldehydes and ketones, including oxidation of aldehydes, reduction of aldehydes and ketones, and then the formation of so-called hemiacetals from reactions of aldehydes or ketones with alcohol molecules. Here we're going to take the opportunity to apply that information. This video assumes that you have already watched the videos leading up to it, namely, that is videos 344, 345, 346, and 347. Let's go ahead and take a look at an example problem. So let's go ahead and take a look at each of these example problems. In the first example problem, we're given O for orthochlorobenzaldehyde reacted with K2Cr2O7 and sulfuric acid. When we see chromium 6, such as is present in K2Cr2O7, what we recognize that as most traditionally is an oxidizing agent. And indeed, in the earlier segment, we learned that a common oxidizing agent is this mixture of sulfuric acid in our K2Cr2O7. So with recognition that this is an oxidizing agent, we remember that oxidizing agents are going to increase the number of bonds between carbon and an electronegative atom, such as oxygen, in turn decreasing the number of bonds between carbon and hydrogen. That is the function that an oxidizing agent is going to carry out in these redox reactions. As we look at orthochlorobenzaldehyde and we draw out the structure of that, we have to ask ourselves what location of that molecule is suitable for oxidation. Drawing that out, benzaldehyde is an aromatic ring. That's our 6-member ring with alternating double bond, single bond pattern. And we can draw that as a hexagon with a circle inside to abbreviate it. And then O-chloro refers to the chlorine atom being in the ortho position. Ortho refers to substitution at the carbon adjacent to the one where the parent name branch comes off. So benzaldehyde refers to the parent having an aldehyde branch. So ortho means that adjacent to that, we would have our chlorine atom. In this structure, the only oxidizable group we recognize is we have this aldehyde functional group. Aldehydes are very readily oxidized, as we learned. And in aldehydes, when we increase the number of bonds between carbon and oxygen and decrease the number of carbon-hydrogen bonds, the location that is susceptible to that is the carbon, which bears the aldehyde group, the carbonyl group there. And specifically what happens here is that the carbon-hydrogen bond is removed because these reactions must lower the number of carbon-hydrogen bonds and increase the bonds between carbon and an electronegative atom, such as oxygen. And that CH bond is replaced with a CO bond to create a carboxylic acid COOH functional group in the final product of this reaction. So I draw this out here now with our COOH group present here. And you should be able to name this molecule based on prior knowledge of naming aromatic compounds. This molecule is a common food preservative called benzoic acid. And if you look at a food label and you see benzoic acid or a compound called sodium benzoate, which is a close derivative of this, that is how this compound is very, very commonly applied. So we recognize that this is our oxidation product, and oxidation has clearly taken place because we've increased the number of bonds between carbon and oxygen and going from the aldehyde functional group to the carboxylic acid functional group. Do be aware that there is an alternative way that you could have written out your product here. You could have had your aromatic ring connected directly to a COOH group. COOH is our shorthand way of representing a carboxylic acid functional group. So be on the lookout for that, and you should be able to recognize that abbreviation as a way that represents a carboxylic acid group. Much like with the aldehyde functional group, we can represent that in shorthand form as simply a CHO group. So a CHO group in our benzaldehyde molecule is equivalent to that aldehyde functional group being drawn out more comprehensively. Let's go on to the next problem. In the next problem, we're faced with 4-hydroxycyclohexanone reacted with potassium permanganate, KMNO4. KMNO4, potassium permanganate, is also recognized as an oxidizing agent. So it is going to behave very analogously to our chromium reagent that we looked at in the first example, in that the function it will carry out is to increase the bonds between carbon and an electronegative atom. In this unit, we're focusing on aldehydes and ketones and alcohols. So therefore, the electronegative atom is oxygen in each of these cases. When it increases the number of bonds between carbon and oxygen, it must decrease the number of bonds between carbon and hydrogen so that the octet rule is filled all the way through. And so looking at the structure of 4-hydroxycyclohexanone, let's go ahead and draw that out. So cyclohexanone will have a 6-atom ring. Do not make this an aromatic ring because we see nothing here to indicate that this has any double bonds in that ring. Cyclohexane indicates to us that these are only single bonds within the ring. The ONE is what tells us that we need to fuse a carbonyl group to that cyclohexane ring, like so. And then at position number 4, we will bond our hydroxy group. The way that we count this is, it will always be the case that the parent name origin of the ketone group is at position 1. We take our path around the ring, 2, 3, 4, and it would be at position 4 here where we will plug in our hydroxy group, our OH group, like so. Now, when we treat this with an oxidizing agent, we have to ask, where are we able to oxidize within this molecule? We have to have a carbon that is directly bonded to an oxygen where we can increase the number of carbon-oxygen bonds by removing a hydrogen atom from that particular carbon. As we look at this molecule, there's 2 possible places that I want you to consider as sites for possible oxidation. That is the carbonyl group here at position 1 and the carbon that's bonded to the hydroxy group over here at position number 4. Now, in order for either of these carbons to be able to be oxidized, they have to have a hydrogen directly bonded there so that we can get rid of that hydrogen during the reaction and increase the number of bonds between carbon and oxygen. Taking a look at position number 1 here, position number 1 has its 4 covalent bonds taken care of as 2 bonds to oxygen, 1 bond to the carbon over here going toward position number 2, and then the final spot to fill the octet is come over here to another carbon atom. So at this spot at carbon number 1 of our ring, there are no carbon-hydrogen bonds, and therefore there is no place there where we can lose a carbon-hydrogen bond in order to oxidize there. So therefore, there can be no oxidation at this particular location. On the other hand, at position number 4, when we look at position number 4, this particular carbon atom, which I will show in blue to draw things out a little more explicitly, to fill its octet, it would have to have a hydrogen here, which isn't shown in the line angle formula. So for its 4 bonds, it has an OH group, 2 carbon atoms, and this blue hydrogen. So with that blue hydrogen in place, it does have 1 CH bond, and that can be replaced with an extra bond to oxygen in order to oxidize the molecule, since we're treating it with potassium permanganate, an oxidizing agent. So we're going to replace that 1 CH bond with a new CO bond. How do we go about doing that? Well, the simplest way and the way that this reaction pathway follows is it converts this carbon-oxygen single bond into a carbonyl group to follow that oxidation reaction. So we take our product here, we'd have our 6-membered ring with our carbonyl group at position number 1, as it was from the start, and I'll go ahead and number that as position 1, coming to position 2, 3, and 4. Position 4 was where our branch to the alcohol group was in the starting material, and we said that's going to get oxidized by replacing the carbon-hydrogen bond that's in blue with a carbon-oxygen bond, and we do that by making a carbonyl group here. So that carbon-oxygen single bond would become a carbon-oxygen double bond here at position 4. So we make a carbonyl group there, in other words. Hence, this reaction effectively converts our alcohol starting material, which I just highlighted that functional group in the starting material, and turns it into a carbonyl group in our final product here, giving us this diketone as our final product. We should actually be able to name this molecule as well. It might seem a little weird because it has 2 ketone groups, but we can handle it. The parent name of this molecule would be cyclohexanone. And then to name the second ketone group there, that is at position number 4, we could refer to that as 4-oxo because carbonyl groups are named as oxo groups with their branches. So 4-oxocyclohexanone would represent a molecule that has a carbonyl group at position 1, and this carbonyl group over here at position number 4 as well of this. This brings us to our next problem, which I would describe as our challenge problem of the day. We start with this molecule, which has both an alcohol group and a ketone group here, with a methyl group on this side. And we're told that the product of this reaction is a hemiacetal. You may be scratching your head and going, wait a minute, I thought reactions of aldehydes and ketones were reactions of aldehydes and ketones with alcohols in order to give hemiacetal products. What gives here? Well, in this particular molecule, we have both necessary functional groups for the reaction present in the same molecule, because at the left-hand end of the molecule here, we have our alcohol group. At the right-hand end, we have our ketone group. So we have both of the groups we need in order to carry out the reaction of an aldehyde or ketone reacting with an alcohol to give a hemiacetal. Since the two groups that are reacting are present within the same chemical structure rather than two separate molecules reacting, we refer to this as an intramolecular reaction. An intramolecular reaction is a reaction where the two functional groups that are reacting are present within the same structure. So in this case, the alcohol group at one end of the molecule reacting with the ketone group at the other end of the molecule. And these reactions generally yield rings. And particularly in the case of the intramolecular reactions of an alcohol and the carbonyl group of an aldehyde or ketone, the product of this will be a hemiacetal that has a ring. This particular reaction is super important in converting between different types of sugars that are present within the body and consumed in food. So we will be learning more about this general reaction later on when we talk about carbohydrates. So taking a look at this particular reaction, we think back to our template of taking an aldehyde or ketone reactant. Since we have a ketone up top here, I'm going to call this a ketone here and define R and R prime as carbon atoms, as is necessary for that to be classified as a ketone and not an aldehyde. We react it with an alcohol, which I'm going to call R double prime OH, where R double prime is a carbon chain or a carbon ring. And then the product of this reaction will correspond to bonding to the carbon atom here, the O alkyl group from the alcohol. So that carbonyl group carbon is going to bond to the OR double prime. That is what was present here from the alcohol. Will end up bonded here to the carbon atom. And then the oxygen atom here will become bonded to the hydrogen atom. And that hydrogen atom originates from over here. So taking a look at piecing this together in an intramolecular reaction, what's going to happen is that the O alkyl group that was bonded to the carbonyl is going to be derived from here. This is our oxygen from the alcohol, and then the carbon chain that's attached to it is what comes through here. So we will connect that around to the carbonyl carbon in order to show what's happening here in this reaction. You could also think of it as follows, which is when we looked at the reaction mechanism, the way that this reaction takes place is that the oxygen atom uses its lone pair of electrons to come and grab hold of the carbonyl carbon because the oxygen is negatively polarized. So it's drawn to the carbon here, which is positively polarized due to the fact that the oxygen is more electronegative in that carbonyl group and is pulling electron density toward itself. So when the oxygen over here comes over and forms a covalent bond to here, and in turn, the pi bond goes up onto the oxygen there, what happens in that reaction step is the formation of a ring, because we are connecting via this map that's showing a covalent bond forming between the oxygen atom of the hydroxy group and the carbonyl carbon. We're showing that we're connecting what was already connected once here a second time through, so that we make a ring system where we have our chain of carbon atoms and then our oxygen here, and then the oxygen bridges back to the other end of this chain. And so we can determine how to go about stitching things together by making a map of where the atoms are located within this. I like to number my carbon atoms to do this. You can number this following the IUPAC rules for numbering or not. You just need to number everything that's there. And I'm even going against IUPAC numbering rules. I'm going to number this oxygen out here because the purpose of the numbering here isn't to come up with the name of this molecule. It's to allow us to piece together where the different atoms will be in the final structure of this molecule. So what I see here is if we are connecting the oxygen atom from over here to the carbonyl right here, what we end up with is a ring that has a total of 6 atoms in it. The carbonyl originated, carbon atom right here as number 1. This CH2 group is number 2. Over here, number 3, number 4, number 5, and number 6 being an oxygen atom. So what I'm going to do is draw a 6-membered ring that has an oxygen atom as one of the 6 atoms in the ring. I am going to go through and number that, beginning with, for convenience, number 7, we said was the oxygen atom. Number 7 was connected to number 6, so I'm going to go around the ring either clockwise or counterclockwise, it doesn't matter which, numbering. 6, 5, 4, 3, 2. And what I'm seeing is that number 2 and number 7 are linked together, and that is indeed the case here. We show that the oxygen atom, number 7, connected to position number 2, and we see that over here that number 7 connects to number 2. I'm going to show that bond for emphasis in red because that corresponds to the bond that we created using this electron pushing arrow here, where we showed that the electrons from the oxygen come over and form a bond covalently to that carbon atom there, creating this covalent link there. So that's going to make our 6-membered ring. And we also need to think about what's connected as well to the ring. So coming over here at position number 2, where we had our carbonyl, at position number 2 of the ring, we would have a carbon-oxygen single bond connected there. I'm going to go ahead and show that at position number 2. So following my map, at position number 2, we had an oxygen bonded here, so I show that. And that oxygen, at this point in the game, if we were drawing out the full mechanism, would have a negative formal charge because in our reaction step, prior we showed the carbonyl group electrons moving up onto the oxygen. The oxygen already prior to that had 2 sets of lone pair electrons to fill its complete octet. So when it picks up another set, like so, by moving the electrons from the pi bond up, it's going to have a total of 3 sets of lone pair electrons. That carbon number 2, which originally was the carbonyl, also is bonded to this methyl group at carbon number 1. So whatever you do, don't forget to include that. So I need to include that as well. And I'm going to label that atom as atom number 1 of our count here. So what we see is that carbon number 1 is connected to carbon number 2. That was true over here as well, and nothing broke those carbon atoms apart. So that legitimately makes sense. And then number 2 is connected to 3, 4, 5, 6, 7. Same thing here, 2, 3, 4, 5, 6, 7. And at position number 7, we did have this hydrogen atom present. So I will go ahead and draw that in, which was there from the start. Like so. There will be a positive charge there at the moment because that oxygen atom has 1 set of lone pair electrons and 3 covalent bonds. If you did the calculation, you would find that would give a formal charge of +1. And then to get to the very final product here, what we do is to get rid of the formal charges, the oxygen atom will have no formal charge if it picks up a hydrogen to become an alcohol group. It can pick up that hydrogen by coming over here and grabbing the hydrogen from right here. That would force the hydrogen-oxygen bond to break, and I'm drawing the electron pushing arrow for that now, showing the electrons from that bond would land on the oxygen so that that oxygen has a complete octet, because these reactions are going to favor ultimately establishing all of the atoms in a relatively stable state, meaning everyone has a complete octet and everyone has no formal charge. Now that I've drawn this out, a way to check your work to make sure that you are on the right track with this is if you've done this correctly, you should absolutely have a hemiacetal group in your product. And indeed we do. Our carbon here is directly connected to an ether group that I've highlighted in pink, and that same carbon is also directly part of an alcohol group, which I've highlighted in blue. And therefore, this structure as a whole would fit the definition of a hemiacetal. If you get to the end and you do not have a hemiacetal product, that means something has gone awry along the way, that you've made a wrong turn somewhere in creating your final product, and it's time to take a step back and ask yourself where things went wrong. Generally, the approach to this is to be very, very systematic by doing things like numbering your atoms, making a detailed map of who's connecting to whom, and then keeping in mind the principle that at the end of the day, you have to make a hemiacetal product. So if you get to here, and you're saying to yourself at this intermediate, I don't really know how to move these electrons around, but all it's asking for is the final product, just think to yourself, okay, we need an alcohol and an ether connected to the same carbon. What's the most reasonable way to do that from here? Well, it would be to make this into an OH group and then get rid of that hydrogen there to make this an ether group to give us the hemiacetal. So while this problem may look a bit daunting, it may look a bit overwhelming, admittedly, taking it step by step and breaking it down makes this type of problem doable. And you should be able to handle, at this point, reactions of aldehydes and ketones with alcohols that are of this sort of level of complexity, doing an intramolecular reaction like we've done here, where the two functional groups are present in the same molecule, or where you're reacting with the alcohol group being a totally separate molecule from the aldehyde or the ketone.